Welcome to Lesson 14D, Stokes terminal particle settling speed. We're going to talk about terminal settling speed in still air, quiescent air. This is just due to gravity, so particles that are just falling due to gravity. We also call that gravimetric settling. In particular, we're going to use a simple approximation and that of Stokes flow, and then next lesson we'll get into the more general case. Before I do that, I have just a quick review. Air properties, we have the ideal gas law, and then we have the Sutherland law to get the viscosity, and these are all the constants for that. We defined relative particle velocity, where v is the particle velocity and u is the air velocity, and so the relative velocity is just the difference between the two. We also had equations for drag on a particle. We have the Cunningham correction factor included, and we have the drag coefficient in terms of Morrison's equation, which is a function of Reynolds number. We also have this equation for the Cunningham correction factor, Newton number, lambda mean free path, and Reynolds number. And last lesson, we developed this equation of motion for spherical particles. What this equation represents is mass times acceleration of the particle. And then this term is the gravity force, and this term is the aerodynamic drag force. So it's really just Newton's law. A comment here that these equations are for standard continuum fluid approximation. However, we've corrected them for free molecular effects for very small particles by using this Cunningham correction factor. The simplest application of all those equations is to calculate terminal settling speed in quiescent air. So what are we talking about? First of all, we have quiescent air, which means that there's no flow. Suppose you have a particle at time t equals 0 that suddenly is just shot at some speed v. What will happen to that in still air? Well, there's no drag force other than what the particle's experiencing because it's moving through the air. So what will happen is that the particle will tend to curve something like that. And as the drag force acts on it, it slows it down, but then it will start falling due to gravity. And eventually, after a little bit of time, it will be falling at some constant speed, which we're going to call v sub t. That's a terminal settling speed of the particle. And this is the speed we want to calculate. I'm assuming here that gravity is down and typically z is up. And here u is equal to 0. There's no airflow. It's quiescent air. Terminal settling speed means that all the forces are balanced so that this thing falls at a constant speed. So Vt is a constant where all the forces on the particle balance. So you would have your net gravity force down, and then you would have your net drag force up since the particle's falling straight down. And those two forces balance so that there's no net force, and therefore it just moves at a constant speed. Now, if we go back and look at this equation for particle motion, we're looking at a case where this little v is equal to capital Vt in the negative z direction. So v is equal to negative Vt times k, where k is the unit vector in the z direction, up. When you have a steady settling speed, there's no acceleration, therefore dv dt is equal to 0. And in that equation, remember we had that little trick where we had VR and then we had the magnitude of VR. Well, we know it's down and we know its magnitude is VT. So this grouping of velocities is simply negative VT squared in the k direction. That's this term here. And as I said, this term was equal to 0. So if we plug all that in, we get 0 equal negative rho p minus rho g plus 3/4 rho CD over C, 1 over dp Vt squared. And that's after a little bit of math. You can see that when the left side is 0, the pi's cancel out here, and 2 of the dp's cancel out since there's a dp squared and a dp cubed, and I combined some of the constants. So a little bit of algebra, and we get this equation, which we can now solve for Vt.
But, sir, the previous equation was a vector equation, and this is a scalar equation.
Yes, you're right, Sean. This is in the z direction, which I forgot to mention.
Okay, thank you, sir.
This is the terminal settling speed for a particle that's falling in still air. And notice that CD is a function of Reynolds number, and this is Reynolds number again. We use Morrison's equation. That looks like a nice simple equation, and we should be able to solve it, but there's a problem. CD is a function of Reynolds number, and Reynolds number is a function of Vt. So you're trying to solve for Vt on the left, but there's a Vt under the square root in this very complicated equation on the right because of the Reynolds number effect. And so this is what we call an implicit equation. You can't just solve Vt equals and then plug in some numbers. Vt is embedded inside that square root inside that CD equation. So the flow is this. CD depends on Reynolds number, RE depends on VT, and VT depends on CD. So you find yourself in a situation where you have to do some kind of iteration to solve for this. I will show you that next time. In other words, for the general case, which is what this equation is, you have to iterate in order to find the solution for VT. Now I'm going to do the simplest case of terminal settling speed in quiescent air, and that is if we make the Stokes flow approximation. I must emphasize that this is an approximation. Pretty much everything we do in engineering is an approximation. But I mean, this is even an approximation of this general equation that we have. What we're going to do, instead of using Morrison's equation, we'll use the simplified equation for Stokes flow. And if you recall, for Stokes flow, this is valid when the Reynolds number is less than about 0.1, and thus CD is equal to 24 over Reynolds number, which is a heck of a lot simpler than the Morrison equation. If we plug in our Reynolds number, we can write this as 24 mu over rho VT dP. Let's plug this CD into our general equation for terminal settling speed VT, and I'll do a little bit of the algebra here. Square both sides, VT squared equal 4/3 rho P minus rho over rho, G dP C over CD, and then let's use this equation for CD. It's in the denominator, so we have 24 mu in the denominator, and then rho VT dP in the numerator. The VT on the right cancels with one of the VTs on the left, so this becomes VT equal 4 over 3, and the 24, I'm going to group those constants all together. Rho P minus rho G, and then there's two dPs, so this is a dP squared. And then finally your Cunningham and your mu. And this grouping of constants becomes 1 over 18, so our final equation is VT is rho P minus rho over 18 G dP squared C over mu. This is the equation for terminal settling speed for Stokes flow approximation. And again, I emphasize that this is an approximation. Specifically, it's valid only if Reynolds number is less than about 0.1. So anytime you use this approximation, you should test Reynolds number to see whether it's less than 0.1 or this equation will not be valid. Let's do an example problem. We have a spherical particle falling in quiescent air, and these properties I picked are just at SATP. You may not always have that in a given problem in a homework or a quiz. And then I have 10 micron particle, and rho P is what we call unit density, same as water, 1,000 kilogram per meter cubed. Calculate the Stokes flow terminal settling speed VT, and then let's repeat for 100 micron particles. To solve a problem like this, first I would find the air properties at this temperature and pressure. Normally you'd have to use the ideal gas law, Sutherland's law, but here our conditions are SATP, standard ambient temperature and pressure. And so we can use the properties of the air that are directly on the equation sheet. You don't need ideal gas law and Sutherland. So for this particular simple problem, we would use rho equal 1.184 kilogram per meter cubed. Mu is equal to 1.849 times 10 to the minus fifth kilogram per meter second. And lambda, mean free path, you would normally have to calculate that as well, 0.06704 microns. Then we calculate the Cunningham correction C. To do that, we first calculate Knudsen number using our lambda divided by our dP, both in microns, so this is non-dimensional. And so the Knudsen number is 0.006704. Plug that into Cunningham equation, and I'll keep 5 digits here, 1.0169. And then finally, we can apply Stokes flow terminal settling speed approximate equation. Remember, this is an approximation. So we plug in the numbers, particle density, air density, and their units are kilogram per meter cubed over 18. dP squared, 10.0 microns. Make sure you watch your units here. I'm going to put these into meters. So 10.0 times 10 to the minus 6 meters squared. That's our dP squared. G, always use 9.807 unless specified otherwise. And then our Cunningham, we just calculated at the top there, was 1.0169, unitless. And then there's a mu at the bottom, 1.849 times 10 to the minus fifth kilogram per meter second. Work out all the units. They turn out to be meters per second. And if you plug this in your calculator, you get VT is 0.00299, 3 significant digits, meters per second. So that's our answer. Notice how small this is. For example, in 1 minute, how far does this particle fall? Well, remember from high school physics, delta Z is equal to VT times delta T. So delta T is 1 minute. VT is known there, so I plug in the values with a unity conversion factor. I get 0.1796 meters, or about 18 centimeters. So it drops only 18 centimeters in a whole minute. So that's moving very slow for 10 micron particle. Remember I said you need to verify. Let's calculate our Reynolds number to make sure we are indeed in the Stokes range. So I'll plug in the numbers there. We use the air density, of course, not the particle density. I've seen students do that. So make sure you use rho of the air when you calculate a Reynolds number. I'm carrying 4 significant digits in my VTs to avoid round-off error. Again, convert dp to meters, plug in your mu, plug in your calculator. I get a Reynolds number of 0.00192, which is much less than 0.1. So we conclude that Stokes flow approximation is valid here. So I can be confident with that value of VT that I calculated. Now suppose we have a much bigger particle, now 100 microns. I'm not going to go through all the math again, just plug in 100 microns instead of 10. You'll have a different Cunningham correction factor and obviously different Reynolds numbers and VTs. If you plug in everything, and this is good practice for you, make sure you get these numbers. I get VT is 0.295 meters per second, much faster, which we expect because it's a bigger particle that's going to fall faster. And then I get RE is 1.89. So we check, is that less than about 0.1? No, it's not even close. So this is not a correct answer. I would say that Stokes is not valid for this case. So that number is kind of bogus. That answer is bogus. I don't trust it. So what to do? Well, we have to go back to our general equation. It was this equation up here, this general case equation with the square root. Unfortunately, we must iterate as I talked about previously, since this is an implicit equation. That's what I'll show you how to do next time. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.